empirical rule of normal distributions. So you can use this rule if the data is normally distributed. So use if data is normally distributed. You know the mean of the data, which is x bar, and you also know the standard deviation of the data, which is s. Now, there are some advantages to this rule. The advantage is that it's an easy way to find probabilities. Some probabilities, but not all of them. But the disadvantage is you can't find complex probabilities. You can only find predefined probabilities. The rule is also known as the 68, 95, 99.7% rule. So the advantage is that it's an easy way to find some probabilities. It is also known as the 68, 95 and 99.7% rule, but the disadvantage is that you can only find predefined percentiles. So I'm going to explain the rule in a second. So the rule goes like so. First, let me draw a normal curve. I think I did a mighty good job on that one. So suppose the data has a normal distribution and you know the mean of the data. So the mean is known. So x bar is given to you. The standard deviation is also given to you. So you have that information. So data is always in the x-axis. And let's say the random variable for which you collected the sample is x. And this sample, when you sketch it out, has a normal distribution. So you know the properties of normal. The mean is in the middle and it has no skew. So x bar is in the middle. And how does the rule go? Well, if I take one step to the left and one step to the right by an amount equal to the standard deviation. So if I move from the mean to the right by one standard deviation, and if I move to the left by one standard deviation, I would reach x bar plus s and x bar minus s respectively. So the rule, the empirical rule, states that for any observation that falls on this interval between x bar minus s and x bar plus s, the probability of occurrence is 68%. So the probability is given by the area over here. So for any observation between x bar minus s and x bar plus s, there is a 68% chance that you can see the observation between x bar minus s and x bar plus s if the data has a normal distribution. So I'm going to write the rule, and this might make better sense when we do an example. So if I move 2 standard deviations to the left and 2 standard deviations to the right, I would reach x bar plus 2s and x bar minus 2s. So the chances of seeing any observation between x bar minus 2s and x bar plus 2s is 95%. And lastly, if you went 3 standard deviations to the left and 3 standard deviations to the right, the chances of seeing any observation between x bar minus 3s and x bar plus 3s would be equal to 99.7%. So, any observation between x bar minus 3s and x bar plus 3s would have the probability of 99.7% of occurrence. For any observation between x bar minus 2s and x bar plus 2s, the probability of occurrence is about 95%, and for any observation that falls between x bar minus s and x bar plus s is about 68%. So the probability of any observation below x bar is 50%, and which is why x bar, the mean of a normal distribution, also corresponds to the median. In other words, 50% of the observations would be below and 50% of the observations would be above. So above you have 50%. If you convert each of these observations to z-scores, you will find that the z-score of x bar minus 3s is negative 3, the z-score of x bar minus 2s is negative 2, the x bar of x bar minus s is negative 1, the z-score of x bar is 0, and there it is 1, 2, and 3. Now, since we have probabilities, we can connect these values that we have defined, x bar minus 3s, x bar minus 2s, x bar minus s, x bar plus s, x bar plus 2s, and x bar plus 3s, and we can actually connect each of these points to percentiles. So using the probabilities that I have, I can find what the percentile of that observation would be like. So an observation, which is x bar minus 3s, has a z-score of minus 3, and I'd like to know what percentile that observation would correspond to. Now, it uses a little bit of algebra, and I know that 99.7% of the observations lie between between 3 standard deviations from the mean to the left and to the right. So 0.15% must lie on the left of x bar minus 3s, and 0.15% must lie on the right of x bar plus 3s. So the chances of seeing any observation over x bar plus 3s would be 0.15%, and the chances of seeing any observation below x bar minus 3s would be 0.15%. So if 0.15% of the observations are seen below x bar minus 3s, then x bar minus 3s must be p.15. It is the 0.15 or 0.15th percentile. So in a similar manner, if you observe that between x bar minus 2s and x bar plus 2s, 95% of the observations will lie between those two quantiles. So x bar minus 2s would correspond to percentile p 2.5. It's 2.5%. In other words, 95% is between the two standard deviations, so 2.5% must be above or 2.5% must be below x bar minus 2s, and 2.5% must be above x bar plus 2s. So if I carry on this way, I'll recognize soon enough that if 68% is in the middle between x bar minus s and x bar plus s, then what I don't have is 32%. So 32% would be below x bar minus half of 32%, which is 16%, would be below x bar minus s, and 16% would be above x bar plus s. Therefore, that would correspond to P16, and that should correspond to P50. If you continue this process, you would find this should be P84. Well, if it's not obvious right now, we can see that if you have 50% of the observations below x bar and 68% is between these 2 points, then it means you have 34% there and another 34% there. So you have 50% up to the midline, so you're adding 34% chance to it, so it would come to 84%. Hence, 84% of the observations must lie below x bar plus s. Therefore, x bar plus s must correspond to the 84th percentile. And if you carry this process onward, you'd find that that is P99.5, and that would be P99.85. And that is the empirical rule. And as you can see that I have connected the observation with its z-score and the percentile. So if the observation is x bar minus 3s, its z-score would be that number, so you'd have -3 would be its z-score, and the percentile would be P.15. This would mean 0.15% of the observations will lie below x bar minus 3s. In a more formal way of saying things, the probability of seeing an observation below x bar minus 3s is 0.15%. Or, this is very formal, the probability of seeing an observation less than x bar minus 3s is equal to 0.15%, which is also 0.0015. So, extending the thought, if I have x bar minus 2s, the z-score would be that number. You'd have -2. The percentile corresponding to x bar minus 2s is P2.5. X bar minus s, the z-score would be -1, and it would correspond to P16. X bar would actually correspond to a z-score of 0, which is the mean of the data itself, and it would correspond to P50, and x bar plus s would have a z-score of 1, and the percentile would be P84, and x bar plus 2s would have a z-score of 2, which would be percentile 97.5, and x bar plus 3s would have a z-score of 3, and the percentile is P99.85. Now, you can write statements similar to what I just wrote here for each and every single one of these cases, and you can just change the value x bar minus 3s to something else, say x bar minus 2s, and you can associate it to a probability. Now, when I do an example right now, it might become quite obvious as to what I'm talking about. So, That is the empirical rule. As you can say, that you can only find probabilities or percentiles at these predefined values. I was able to do it at x bar minus 3s. I was able to come up with a z-score. I was able to come up with a percentile. But if I moved by a value other than -3 to the left, for instance, instead of moving exactly by one standard deviation to the left, if I moved half a standard deviation to the left, I don't know what the probability would be. I don't know what percentile that number would be, and it's not obvious from this rule, and which is the disadvantage of the empirical rule of normal distributions. So if you want to find exact probabilities, we need a more complicated approach, but then we should always know that there is no such thing as a free lunch, and we have to put extra effort if we want to find that probability. So that being said, I'm going to move on to an example. So keep in mind that if we want to use the empirical rule, the data must be normally distributed and you must know its mean and standard deviation. So here's an example. Let's say suppose the average calorie intake, let me rephrase the problem. I'm going to say suppose the calorie intake of a 20-year-old male is normally distributed with mean 2,400 kilocalories per day and has a standard deviation of 100 kilocalories per day. Let's assume that the study was carried out in the US. So we would actually find a couple of probabilities using this single statement. So first off, let's identify the random variable. The random variable here, x, is nothing but the calorie intake of a 20-year-old male. And we know that this random variable x has a normal distribution, and we know its parameters with x bar equals 2,400 kilocalories per day and s is 100 kilocalories per day. So in a problem like this, and if you want to use empirical rule, it's always best that we sketch the distribution out. So I'm going to go ahead and sketch it out, and let's say we'll create a problem first before we draw the sketch. What is the probability that a 20-year-old male would consume at most 2,500 kilocalories per day? Suppose that is a question that we wanted to answer, and best way to learn empirical rules is by drawing the bell curve as necessary. And I know that the mean is 2400 kilocalories per day. And I'm going to write the standard deviation right below it. The standard deviation is 100 kilocalories. And the question wants to know the probability that a 20-year-old male would consume at most 2500 kilocalories. So if 2400 is over here and you take one step to the right, I get to 2500. So what percent lies below 2500? How likely is it that we observe a person who would consume at most 2500 kilocalories per day? Now, we know from our previous descriptions that if I go one standard deviation to the right, it would correspond to P84. So one standard deviation to the right corresponds to P84, which would mean 84% of the probability would lie below x bar plus s, and 16% would be above x bar plus s. So the probability of seeing an observation for x, which is the amount of calories that a person would consume, a 20-year-old male would consume, is x. And if you want to know how likely is it that a person would consume at most 2500, in other words, starting at 0 all the way up to 2500 calories, based on this particular description and based on this distribution, that probability would be 84%, because 84% would be below that line and 16% would be above. So the probability that a 20-year-old would consume at most 2500 kilocalories per day is 84%, or it is just 0.84. So using the same problem, we can also say also find the probability that a 20-year-old male would consume at least 2500 kilocalories per day. Now, we already know at most is P84, at least is anything above 2500, so it's 2500 or more. So what percent lies above 2500 according to our distribution? Since this number is P84, 84% lies below 2500 and 16% lies above 2500. Therefore, the probability that a 20-year-old male would consume at least 2500 kilocalories per day is 0.16, or 16%. Suppose if someone asked you, based on this data, what is the z-score of 2500 kilocalories per day of the observation? Well, I know that 2500 was one standard deviation to the right from the mean, which is 2400. 2400 would correspond to a z-score of 0. So since you moved one standard deviation to the right, 2500 would have a z-score of 1. you can go back to our table that we created initially, and if you create a table such as this one, you can immediately come up with the z-scores and the observations and the corresponding percentiles. Let's go ahead and complete that table using this particular example. So let's say we have x bar as 2400. So if I moved 3 standard deviations to the left, let's say that is our line for the calorie intake, 2400 calories over here, and 1 standard deviation to the left would be 2300 calories. 2 standard deviations to the left would be 2200 calories, and 3 standard deviations would bring you to 2100 calories, and 1 standard deviation to the right would be 2500, 2600, and lastly 2700 kilocalories per day. And that point would correspond to x bar. That is x bar plus s, x bar plus 2s, x bar plus 3s. This is x bar minus s, x bar plus 2s, excuse me, that is x bar minus 2s and x bar minus 3s. Just by looking at this, I can immediately connect the observation to a z-score. The z-score of 2100 is negative 3. The z-score of 2200 is negative 2. The z-score of 2300 is negative 1. Z-score of 2400 is 0, 1, 2, and 3. Now, if we want to find the percentiles, what percent of observations would lie below 2100 kilocalories? In other words, what is the probability that a 20-year-old male would consume at most 2100 calories? It's about 0.15%. So that number would correspond to p.15. That would correspond to p 2.5. That should correspond to p 16 and p 50, p 84, p 97.5, and p 99.85. So, since the data is normally distributed with the parameters that is given in the problem, I can complete something like this immediately. This gives me a good idea as to what the probability is between two values. So for instance, if I want to know the probability that someone would consume between 2100 and 2600 kilocalories per day. So what is the probability that a 20-year-old male would consume between 2100 kilocalories and 2600 kilocalories per day? So first I need to know the probability that the 20-year-old male would consume at most 2100 kilocalories. So if you go back to our real number line, which I drew, 2100 is over here and 2600 is over there. The probability that a person would consume at most 2100 all the way up to 2100 must be 0.15%, because 2100 corresponds to P.15. So the probability that someone would consume at most 2100 kilocalories per day is just 0.15%. Now, using the same logic, what is the probability that someone would consume at most 2600 kilocalories? Well, starting from anywhere below 2100 all the way up to 2600 kilocalories should be 99.85. 97.5. 97.5% of the observations must lie below 2600, according to our quick sketch that we completed a minute ago, several minutes ago. So the probability of seeing any observation below 2600 kilocalories is 97.5%. So the probability of seeing any observation below 2100 kilocalories is 0.15%, and any observation below 2600 is 97.5%. And I'd like to know what percent is in between. So I just have to do quick algebra to find this out, because if 0.15% is below this number and 97.5% is below that number, I'd like to know what lies in between. Well, if all of this probability is 97.5% and that is 0.15%, that has to be 97.5% minus 0.15%, which would give me 97.35%. So the probability that a 20-year-old male would consume between 2100 and 2600 is 97.35%. So you can do problems with normal distributions as long as you know the empirical rule of normal distributions. Now, you have to keep in mind that writing this rule is possible only as predefined values, predefined steps from the mean. So you can go one step from the mean equal to an amount of one standard deviation. So one standard deviation to the right, one standard deviation to the left, two standard deviations to the right, and two standard deviations to the left, and so forth. But you can't find other probabilities, you can't find other z-scores more accurately. For example, if someone asked you what is the z-score of the observation based on this picture, observation, let's say 2350, all I can tell them is it's going to be somewhere between 0 and -1, but I can't exactly tell them what that number is using this picture. So in a similar way, if someone asks you a probability as to what is the probability that a 20-year-old male would consume at most 2,450 calories. Let's just make an example out of this before we conclude. So suppose someone asked you, well, what is the probability that a 20-year-old male would consume at most 2,450 kilocalories per day. Well, this is kind of an kind of a disadvantage of normal distributions, because according to our diagram or sketch that we did, we started the mean and we took one step equal to one standard deviation to the right, 2 steps, 3 steps to the left, so I know the percentile of this observation, which is 2.15. I know the percentile of that observation, which is 2.5, and that is P16, P50, P84, P97.5, and P99.85. But in this question, we'd like to know the probability that someone would consume below 2,450. So I'd like to know that probability. So what do you think the answer is? Okay, the answer is unknown if you want an exact answer, but the answer is approximately 70%. It's just a guess. I'd probably guess it's somewhere between 50 and 84%, but I don't know exactly what that number is, because the empirical rule does not tell me what that value is. So this is a disadvantage of the empirical rule, because it can only tell me probabilities at predefined points, but not at all points. And there are other ways to do this, but we can talk about it in a different video, which would involve normal distributions and finding probabilities using normal distributions. I hope you learned something about the empirical rule of normal distributions from this video. Go back and look at these problems and look at the table and look at the sketch to get a better understanding. Thank you.